Our first part of discussions for today would be the normal distribution. We also refer to the normal distribution as the bell curve. So if we go and we take a look, a couple pages ahead, we get a beautiful picture of our bell curve. So here is our bell curve. It is in your notes. The bell curve is used for when you have a normal distribution. And whenever you're collecting data, you want it to fall within the bell curve. You want it to have a normal distribution. So what happens... Yes. The middle of your bell curve at that 0, that is where your mean goes. So within each problem, your mean value changes, but it always goes right there in the middle. So that 0 just represents the mean. It's not the actual mean value. No. Not on the normal distribution, no. So then these other numbers here represent the standard deviations. Those are the standard deviations. So that just tells you how far away from the mean value that you are. So if you have a negative standard deviation, that means you're just below the mean. If you have a positive standard deviation, that means you're going to end up being above the mean. So depending on what kind of problem you're dealing with, if you're dealing with, say, a test grade and you're 2 standard deviations above the mean, that's awesome. That means you did really well. If you're 2 standard deviations below the mean, that means you didn't do so hot. Well, it depends on what the grade is. There's so many different pieces of data we need for that. So, these percentages inside of your normal curve, that represents what percentage of your data should fall in that range. So between your mean and half of a standard deviation, 19.1% of your data would fall in there if it has a normal distribution. Between half a standard deviation and 1 whole standard deviation, 15% of your data will fall just between those two. So if you're trying to find between 0 and 1 whole standard deviation, you would add these two together. So that would be 31 or 34.1% would be 1 standard deviation above the mean. That's how much of your data falls there. All right, so let's go back to our first problem here. For a population that is normally distributed, and as soon as you see that phrase right there, you should be thinking in your head automatically that means it fits on a bell curve. So for a population that is normally distributed, find the percentage of the population that lies, and then part A wants us to do within 1 standard deviation of the mean. So let's go back to our bell curve. We're going to be flipping back and forth a lot. Yes. So, 1 standard deviation means we go from 1 below the mean to 1 above the mean. They want us to find the percentage that falls within 1 standard deviation of the mean. So as we said before, that means you could be below by 1 or you could be above by 1. So we got to add these 4 percentages up. All right, let's add this up. 68.2. So with a normal distribution, within 1 standard deviation of the mean will always be 68.2%. That's not going to change.
68.2% of the population?
68.2% of whatever you're dealing with will always be within 1 standard deviation of the mean. So next one, they want us to find within 2 standard deviations of the mean. So -2 up to +2. We got to add up all those percentages. Yeah, we could do that. So let's see here. We got 4.4, 9.2, 15, 19.1, and then it starts repeating. So I will do 2 times 4.4 plus 9.2 plus 15 plus 19.1. Let's figure out what that is. .4%. So is it very likely you're going to have anything beyond 2 standard deviations? No, it's not very likely that that's going to end up happening. All right, so next question is a little different. They want to know more than 3 standard deviations away from the mean. So we're not going to add up the middle because we're looking for the ones that are more than 3 standard deviations. So if we go back to our bell curve, that means I'm looking here because this is more in the negative direction. And we're looking here because that's more in the positive. So yeah, it would be 0.1 plus 0.1. So that ends up being 0.2%. So it's very unlikely you're going to be beyond 3 standard deviations. Yes? Yes. So now they want to know between 1 and 2 standard deviations above the mean. So we're looking at just the ones above the mean. It's between 1 and 2 standard deviations. So here's my 1. Here's my 2. What 2 percentages do we add up? 9.2 and 4.4. So 13.6% of our data falls between 1 and 2 standard deviations above the mean. All right. As can be easily seen from exercise 1, the majority of any normally distributed population will lie within 1 standard deviation of its mean. And even further than that, a vast majority of them will lie within 2 standard deviations of our mean. That was our 95.4. So a whole variety of problems can be solved if we know that a population is normally distributed. So let's look at example here. At Arlington High School, 424 juniors just took the SAT exam. On the math portion of the exam, the mean score was 540, and there was a standard deviation of 80.
540, isn't that terrible?
So if the scores on the exam were normally distributed, let's answer the following questions. So they want to know what percent of the scores fell between a 500 and a 660. So we got to use our bell curve because they told us it was normally distributed. If you have pencil, I highly recommend writing in pencil. So our mean score was 560. So that goes right there. No, that's not 560. I'm thinking of a different problem. No, it's 560. It's 540. Yep. Nope. Normally distributed will always be this curve. Back to our bell curve. So our mean is 540. So that is our middle number there. Our standard deviation again was a what? Standard deviation was an 80. Since our bell curves go by half though, what would half of our standard deviation be? 40. So if I am going above my mean, that means that my score for half a standard deviation above would be 580, because I would just add my standard deviation to it. This would be 620, and then 1.5 would be 660, which is one of the numbers we wanted. They wanted between 500 and 660. So there's 660 at 1.5 standard deviations. We got to figure out where 500 is. So now we're going to subtract because we're going down. Oh, and I'm already there. Subtract 40 once. There's my score of 500. Yeah, negative a half. So negative 0.5 to 1.5, that's where my scores will fall. So we've got to add these percentages up in between them. So 19.1 plus 19.1 plus 15 plus 9.2.
Are we always going to have this?
Not on your regions.
Do we have to remember this?
Add them up. What do we get? Not 0.6. 62.4. So 62.4% of the students scored between a 500 and a 660. So part B, they want to know how many students that actually was. So we're going to take our 424 juniors and multiply it times our percent of 62.4, but I move my decimal over 2 places to the left when I multiply. So what do we get?
That's the 0.624.
So this would round to 265 students. But this is data, so it's different than exponential growth decay. Data, you round normal.
Most of the time we can finish the test. What did you get on your SAT?
Next one. If Evan scored a 740 on her math exam, what percent of the students who took the exam scored better than she did? So first thing we have to do is figure out where 740 falls on our bell curve. So we left off at 660. So if I add another 40, 700 would be at my 2 standard deviations above. So 740 is right here at 2.5. So we're looking for the ones who did better than she did. All of the ones to the left did worse than she did. So what percent did better than she did? 0.6%. No.
So, is the bell curve the same for every?
If it is a normally distributed problem, it'll always be the same.
Did they give us that?
No. Part D, they want us to figure out how many students did better than she did. So we're going to take our percent, multiply it times the 424. .544, which rounds to 3. Only 3 students did better than she did.
Those smart students,
Yes.
they're going into jail.
Oops, too far.
Maybe Evan's going to jail.
Let's go to the next one. The heights of 16-year-old teenage boys are normally distributed with a mean of 66 inches and a standard deviation of 3. If Jabari is 72 inches tall, which of the following is closest to his height's percentile rank? So percentile, if you remember, that's people who scored lower than you did. So on your bell curve, it would be all the percentages to the left of wherever you are. There is a little bit of an easier way to figure out what standard deviation you're going to fall at on the curve instead of sitting there and always adding and subtracting your standard deviation. So it's your score minus the mean divided by the standard deviation. And again, that helps you figure out where on the bell curve you fall a lot faster than just adding and subtracting up along the curve. So for Jabari, he's 72 inches tall, the mean was 66, standard deviation of 3. So subtract, divide, we get that he is 2 standard deviations above the mean. So if we go take a look at our bell curve, he is 2 standard deviations above the mean. So he's right here. We are looking for his percentile rank, which means we need all of those percentages to the left. But that's going to take a while. So we could add these ones on the right and subtract it from what? 100. So 100 minus 1.7 plus 0.5 plus 0.1. Let's see what we get. So it's the 98th percentile. He's pretty tall, apparently. Yes, it is 6 feet. Good job. All right, so 4, the amount of soda in a standard can is normally distributed with a mean of 12 ounces and a standard deviation of 0.6 ounces. If 250 soda cans were pulled by a company to check volume, how many would be expected to have less than 11.1 ounces? So let's first figure out where would 11.1 ounces fall on our normal bell curve. All right, anybody figure out yet where our 11.1 falls on our bell curve? I'll give you a hint, it's going to be negative.
Negative 8.9?
No.
Negative 1.5.
Negative 1.5. So this is at negative 1.5 in our bell curve, so it's 1.5 standard deviations below our mean. So we want the ones that are going to be less than that. So we want to the left of the negative 1.5 on the bell curve. So that means we would be adding the 0.1 plus the 0.5 plus the 1.7 and plus the 4.4.
Why is 1.7 and 4.4?
Because we're going to the left of negative 1.5. But that's not one of our answers, because we still have to do one more step.
Multiply 6.7 by 250.
Yes. So let's use 0.067. And that'll give us the actual number of cans instead of a percentage.
16.75.
So that would round to, so 17 cans would be expected to have less than 11.1 ounces. All right, 5, biologists are studying the weights of red king crabs in the Alaskan waters. They sampled 16 crabs and compiled their weights in pounds as shown below. So determine the mean and the sample standard deviation for the crabs. Round both to the nearest tenth. So I'm going to give you guys,
For my mean, I got 12.6.
yes. Standard deviation,
1.5.
1.5.
What did I do wrong here then? Yeah, thanks. I got the
So part B, they want to know, why does this sample indicate that the population would be well modeled using a normal distribution? We need to explain. So let's figure out what one standard deviation above and below would be. So let's add 1.5 and subtract 1.5. So if I add 1.5, what do we get?
You get 14.1.
14.1. If I subtract 1.5, 11.1. So let's figure out how many crabs are between 11.1 and 14.1, including those numbers if they're there. Hold on, we'll just circle the ones that are in between those. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 out of the 16. What is that as a percent? 11 out of 16 as a percent.
9%.
So we need to include
68.75%.
68.75.
Just round up.
So on our normal distribution, one standard deviation we found on the front to be 68.2. Isn't that pretty much it? That was from our normal bell curve. We already added up one standard deviation on the front. It was 68.2. So 68.75 and 68.2, those are close enough, so we can say that it is.
How come this time it doesn't include 11.1?
So our the expected percent is almost the same. All right, see, assuming your mean and standard deviation from part A apply to a normally distributed population of crabs caught in Alaska, what percent will fall between 9.6 pounds and 15.6 pounds? So first thing we got to figure out is where would these fall on our bell curve? So like we were doing above, 9.6, subtract your mean, divide by your standard deviation. Let's figure out where that's going to fall on our bell curve. Since it's less than a mean, I know it's going to be negative. -2.
I did that in my head.
Me too. All right, let's figure out where 15.6 is going to fall on the bell curve. So we subtract the mean, divide by the standard deviation.
2.
Fall at +2. We have already figured out once on the front, -2 to +2 is what percent? Two standard deviations from the mean was what percent? 95.4%. So 95.4% will fall between 9.6 and 15.6. So then our last one on this page, part D, if fishermen must throw back any crab caught below 10.4 pounds, approximately what percent of the crabs caught will need to be thrown back if the weights are normally distributed? So again, first thing we got to figure out, where does 10.4 fall on our bell curve? So subtract the mean, divide by the standard deviation. Let's see where we fall. -1.5. So it was like -1.46. So we rounded up to 0.5 because we have to do halves. So we got to add up the percentages that are lower than -1.5. We may have, already done that. .7%. So 6.7% of them are going to be thrown back because they don't weigh enough yet. All right, next thing we're going to be talking about are z-scores. But you've already started calculating z-scores. That's what we were doing to figure out what standard deviation that we fell at on the bell curve. Here is the official definition for your z-score, just so you can get used to seeing the symbols. The x sub I, that's your score or your height or your weight, depending on what the problem is dealing with. This little funky U thing, that is your mean. That is the symbol they like to use for mean sometimes, called mu. And then, of course, this little guy down here, we've seen him before. That's our standard deviation. So to get our z-score, it's whatever your score is minus the mean divided by the standard deviation. As I said, we were already doing this on the last page. Positive means you are above the average. Negative means you are below average. So first part, all we're going to do is practice calculating z-scores. So we got a mean height of 62 inches, standard deviation of 3.2. first kid is 66 inches, so we're going to do 66 minus 62 divided by 3.2. So let's figure out what his z-score is. To the nearest hundredth. Z-scores will always be to the nearest hundredth. 1.25.
And then we just leave it at that.
And that's it. So B, our next z-score. 57 minus 62 divided by 3.2.
Negative 1.56.
Negative 1.56. And our third z-score, 70 inches minus 62. 2.50. So we got to go to the nearest hundredth. So our z-scores, they give us very accurate standard deviations, especially when we can go to the nearest hundredths. As you can see, we're going to start getting some that aren't falling on the halves. It's not always going to be 1.5 or negative 1.5. We got a 1.25. We got a negative 1.56. So we're going to learn how to be able to calculate the percentage of getting that score, which is what we were doing before with our bell curve. It'd give you your percentage of getting that score either above or below. But we're going to be able to do it for more than just the halves also. So let's first look at number 2. We got Jeremiah, who took a standardized test that had a mean score of 560 and a standard deviation of 45. He doesn't remember what his score was, but he knows he has a z-score of 1.84. So they want us to figure out what his actual score was to the nearest whole number. So just like we did before, it's the same formula, only we know his z-score this time. So 1.84 is going to equal his score minus the mean divided by your standard deviation. So what can we do to figure it out? You can multiply both sides by 45. You can put this one over 1, cross multiply, either one. So what do we get when we multiply 1.84 times 45? I heard somebody say it. I got to say it louder. 82.8. And then what do we do with our 560? So we got to round it, though, to the nearest whole number. So he got a 643. So now once we have our z-scores, again, we get the z-score to help us figure out the probability that somebody is going to get that score, or to help us get a percentile rank, which then compares that score to everybody else, and it tells you who scored lower than you guys, than that person did. So when you have z-scores, or standard deviations, that are not the halves, like these ones, there's two ways we can figure out what that percentile is going to be, or what the probability is going to be. One way is by using this beautiful chart that you have in your packet. So here on the left side, you have the first tenth of your z-score, and then going up across the top, that's where you get your hundredths, and you meet in the middle, and that's what your z-score probability ends up being. So let's practice using this.
So if it was like 0.12, you go to like the
0.1 and then over to 0.12, or over to the 2. So number 3, we have the lengths of full-grown sockeye salmon are normally distributed with a mean of 29.2 inches and a standard deviation of 2.4 inches. They want us to find the z-scores for the salmon whose lengths are 25 inches to 32 inches, round to the nearest hundredth. So first we're just finding some z-scores. Z-scores are easy. Let's start with the 25-inch salmon first. So 25 minus our mean of 29.2, divide by our standard deviation of 2.4, and let's get our z-score to the nearest hundredth. 1.75. So now we got to do it also for 32 inches. So 32 minus 29.2 divided by 2.4.
1.1.
So 1.17. So part B, they want us to use the z-score table to determine the proportion of the salmon population to the nearest percent that lies between 25 inches and 32 inches. So, we draw a bell curve, which a lot of times they ask you to kind of draw a picture, which means they're looking for you to draw the bell curve. Right here in the middle, that is our mean of 29.2. So my 25 is going to fall over here to the left. My 32 will be like over here to the right. Well, no, the 25 is at my negative 1.75. So what I have to figure out is we're going to figure out the proportion or the probability of getting the 25 between the mean and the 25. And then we're going to figure out this one over here, and then you add the two of them together. So what our z-score table does is this is the probability of getting that value from the mean to that number. So like here, right here is my visual picture for you that represents it. So it's from the mean to whatever your z-score is. So that's why we got to find the two of them. So our first one was negative 1.75. So here's our 1.7. And then if you look at your top, this is 0.00. This is 0.01, 0.2, 0.3, 0.4. There's our 0.5. So that's what the first one's going to be. 0.4599. So this part of our bell curve right here is 0.4599. That was our number off our chart. So now we have to figure out for our other z-score of 1.17. So I go back to my table. So here's my first part, 1.1. And then I got to go over for my 7. Here's my 7. They meet right there, 0.3790. So now when I add those two together, that gives me my total proportion, my total percent. So 0.4599 plus 0.3790 gives us 0.8389. So as a percent, that'd be 84%. A little bit more work involved when it's not a nice little half standard deviation there. So 84% of the salmon are going to be between 25 inches and 32 inches. So that's the way I had to do it, because we always had to use our z-score charts. I'm going to teach you another way to do it.
Is it easier?
Yes.
A lot easier?
So what we're going to use is what is referred to as normal CDF. So you need to know 4 numbers for your normal CDF, what they call the lower bound, the upper bound, your mean, and your standard deviation. So we're going to use normal CDF for this next problem. So if the scores on a standardized test are normally distributed with a mean of 560 and a standard deviation of 75, answer the following questions. Mean of 560, standard deviation of 75. So part A, find the probability that a test picked at random would have a score larger than 720, round to the nearest tenth of a percent. So you still want to kind of draw a little picture of your bell curve. Right there in the middle, there's my 560. So which side would 720 fall on, the left or the right? The right side. So I'm just going to kind of estimate my 720 would be about there. And we're looking for the scores larger than it. So that means we're looking for the scores to the right of my 720. Is everybody with me so far? So we're looking for that area right there that I shaded in. So we're going to use our normal CDF to do it. And when you use normal CDF in your calculator, you got to write down what you're typing in because that's going to be your work shown for these ones. So as I said, we need lower bound, upper bound, mean, and standard deviation. So for this problem, our lower bound is the 720 because that's the lowest part where the shading is. So we're going to put 720 in there. Since this one continues off the bell curve and we kind of really don't know where it ends, you kind of have to exaggerate your upper bound. So I just generally write 5 nines in there. So 99, 9999. You got to pick a ridiculously large upper bound for that. Our mean is 560, and our standard deviation in the problem is 75. So now let's go to our calculator. So in the calculator, you're going to go to second vars.
Second what?
Vars.
Where's that? Vars. V-A-R-S.
All right, let's try this again. So second vars, and then your second one here, normal CDF. Now some of you might have a nice little list asking you for your lower, your upper, your mean, your standard deviation, so then you just fill in those numbers. If yours look like mine, you have to type it like we have it written on the paper. Comma. I forgot now what our mean was. It's above the 7. But if you have a list, you don't need the comma.
Yeah, is that little upside down H?
That's the mean.
560?
Our lower bound was the 720. That's why you've got to write down what I had up on the notes.
Oh, it's right here. Well, then take, then what? What's the lower number?
720. You should have it written on your paper.
Yeah, I heard that. But now, you're just using commas to separate them?
Yeah, I have to use commas because I don't get a nice little list. And then we hit enter. So you should get 0.01644866368. So generally for these ones, we go to the nearest thousandth. Okay. So 0.0164. And then nearest tenth of a percent would be 1.6%. Let's try our next one. I'm going to set up my normal CDF. Draw my little bell curve. Still got 560 in the middle. I didn't even read the problem yet, but it's still 560 in the middle because it's still part of the same thing. We're looking for the probability that a completed test picked at random will have a score less than 500. So 500 would be over here. So we want less than 500, which means we want to the left of the 500. So this continues all the way off the paper. So do we really technically know our lower bound this time?
No.
No. So we're going to use negative 99999. We just pick a really extreme lower bound number to use. That one always works well. Our upper bound would be 500, because that's where our little shading stops in our picture. And our mean and standard deviation have not changed. Still 560, and then still 75. So go ahead, if you haven't already, type that in your calculator to practice. Second vars, choice 2. Second vars, negative 1, 2, 3, 4, 5, comma 500, 560. So that's 0.2118, so the nearest tenth of a percent would be 21.2%. It's time. Our lower bound is 500. Our upper bound is 600. We're trying to figure out what's the percentage that we're going to get in between the two of them. So lower bound 500, upper bound 600. Average is 560. Standard deviation is still 75. So go ahead, type that in if you haven't already. Oh, please don't. .49 what? 1, 2. And then they didn't ask us for a percentage. They just said find the probability, so we're just going to leave it as a decimal. If they want a percentage, you give them percentage. If they don't ask for it, you leave it as a decimal. All right. Next one. So again, draw my bell curve. Put my little 560 right there in the middle. That's my mean. This time we're going between 600 and 700. That little shaded part in there. So what's our lower bound?
600.
Upper bound? Mean? And standard deviation? 75. So go ahead, type that in your calculator. Because it's still the same problem. So it's not going to change. What is it? 0.2659. Did they ask us for a percentage that time? No. Nope, so we leave decimal. All right, last two questions. The average weight of a full-grown beef cow is 1,470 pounds with the standard deviation of 230 pounds. If the weights are normally distributed, what is the percentile rank of a cow that weighs 1,750 pounds? So if we have our little bell curve, 1470 is right there in the middle, because that is your mean. So 1750 is going to be higher than that. And again, percentile rank means it's going to include all of those values less than that. So yes, we can use normal CDF. But which two can we eliminate right away? 3 and 4. Because it's higher than the mean, so it has to be higher than 50. Because 1750 is higher than your mean, your percentile rank has to be higher than 50. Because your mean is the 50th percentile. So we will use normal CDF. Do we know our lower bound? No. So you just put a negative 99999. Our upper bound would be the 1750. Mean is the 1470. And our standard deviation is 230. So then our percentile would be
89.
89th percentile.
Let's say 230.
Yes. So the one thing though about the calculators, you don't even need to consider a z-score at all. It's taking care of all of that for you, and it's basically going through and using the chart. So let's have you practice these last three. You're using your normal CDF. Mean is 12.2. Standard deviation is 0.6. So you're going to be determining the probability of using this one. We want a bottle greater than 13 inches. I'm sorry, 13 ounces. I misspoke. Well, that's what it's supposed to technically be, but when they calculated it out, the mean was 12.2. So really, this 12 ounce, extra information we're not going to be using. So 13 ounces is going to end up being greater than our mean of 12.2. So we want greater than 13 though, so we went over here to the right. This is why it's always good to draw the little bell curve picture to make sure you get the right information. So what is our lower bound going to be? No. Because we want to go to the right, our lower bound would be the 13. Our upper bound would be positive 9999. Your mean is 12.2 and your standard deviation is 0.6. 0.0912. Nope, because they didn't ask for percent. They just wanted the probability, so we leave it like that. Go ahead, try to see if you can figure out the other two on your own.
0.228.
Very good, 0.0228. How about for C? Well, what's after the 7? So it makes it 0.96 or 0.5698.